In this video, we're going to take a look at the graphs of logarithmic functions specifically. So right at first here, I just want to look at some properties that graphs of logarithms have. And I really should have put a ready-made graph right here. So since I didn't, if you can with me here, just make a set of axes. And what I want to remind us of is something that we looked at in a previous section, which is, how does the logarithmic function compare to the exponential function graph? And so let's make this concrete. Let's talk about the function 3 to the x. Okay. And what I just want to make note of here is that we're going to remember that this function always goes through the point 0, 1, and it also goes through the point 1, 3. And let's see, we'll use a different color here, and then basically the function looks like this. Okay, and remembering that the logarithm is the inverse of an exponential, we know that these functions have to be symmetric with one another about the line y equals x for one. And then remember, a function and its inverse, their inputs and outputs are just switching. So what that means is that if 0, 1 is on the graph of f, then 1, 0 is on the graph of f inverse. Okay? And if 1, 3 is on the graph of f, then 3, 1 is on the graph of f inverse. And if I have a horizontal asymptote on my exponential function, when you reflect that about the line y equals x, that should become a vertical asymptote. And so this is the look of my inverse to f of x equals 3 to the x. And so we're talking about a base of 3, so that means we're talking about the function log base 3 of x. All right, so notice we plotted 1, 0 and 3, 1. So that's just 1, 0 and b comma 1, whatever the base is. Those are always going to be points on the graph of f of x equals log base b of x. There's a vertical asymptote always at x equals 0. You can see that it has a domain of 0 to infinity. Right? It never actually touches 0 because it never touches the vertical asymptote, but it gets as close as it wants. So parentheses 0 to infinity. And then the range is negative infinity to infinity. Even though it starts growing really slowly out here, it does ultimately grow forever. And so there's no restrictions on the range at all. So generally, when we want to graph a logarithmic function, it's going to be sufficient to basically graph these 2 points. And we'll also look at transformations of logarithms, so it might be like these 2 points transformed, for example, stretched or shifted or that sort of thing. But graphing these 2 points and knowing where the vertical asymptote is generally going to be enough to get an accurate picture of a logarithmic function's graph. All right, so let's do an example here on the next page. And we're going to take a look at 2 functions, the log base 2 of x and the log base 1/2 of x, and see what comes out here. Okay, so based upon what we learned on the last page, we definitely know, we'll do this one here in green, for log base 2 of x, the point 1, 0 and the point 2, 1 are definitely on the graph. Now, since this is the first one that we're doing, it might be not a terrible idea to go ahead and make a table. All right, so we just put in x equals 1, the log base 2 of 1. We know that's equal to 0. The log base 2 of 2 we know is equal to 1. And remember, the thought process you're going through is you're saying, what number do I raise 2 to the power of to make 1? And the answer would be raise 2 to the power of 0 to make 1. What do I raise 2 to the power of to make 2? Well, you'd raise it to the first power. Okay, let's do a couple more here. Now what we want to think about is these x values should be powers of the base. Okay, so I'm not going to put 3 in here because 3 is not a power of 2. However, 4 is a power of 2. So let's plug 4 in and see what that gives us. And what I would remind you of here is if you're kind of getting lost in the definition of a logarithm, remember you can always resort back to saying this. I want to know what the y value is of this graph. So y equals the log base 2 of 4. You can always rewrite that in its exponential form. So the base raised to the y is equal to 4, right? And then looking at that, of course, 2 squared equals 4, so that means y must equal 2. So I know that that's equal to 2. And then let's just do one other one here. How about, so I can put a point here, and then let's go to the left of 1. So let's think about what would be convenient. Again, we're thinking, what's a power of 2? So I'm going to use 1/2. So the log base 2 of 1/2. Okay, what's that equal to? And again, if you're not sure about where to go next, you say, let's give a little space here. Y equals the log base 2 of 1/2. So in exponential form, that's 2 to the y equals 1 over 2. But we know 1 over 2 by our exponent rules is 2 to the negative 1. So therefore, this must be negative 1. So when x equals 1/2, y equals negative 1. And then finally, using the fact that we know there's this vertical asymptote running through the y-axis here, we know that from down here it's got to approach that vertical asymptote, and then up here we head off that way. So there's our log base 2 of x graph. All right, now what if we put 1/2 as the base? Okay, again, let's use that fact that we learned on the previous page. So we're definitely going to, let me rewrite it here, f of x is the log base 1/2 of x. So we're definitely going to put in the point 1, 0. And then we're going to put in the point 1/2, 1, right? So we've got to have both of those points, right? And again, where's that coming from? That's coming from the fact that you always have 1, 0, and then whatever the base is, comma 1. All right, and at this point, you might look at this and see pretty much how to graph this thing. But again, we haven't done a lot of these, so let's do a couple more points than just those two. So we've already graphed when x equals 1/2, we know that the y is 1. When x equals 1, we know that the y is 0. Okay, so how about let's try 2. Okay, so we're taking the log base 1/2 of 2 is our y value, but in exponential form, that's going to be 1/2 to the y equals 2. All right, so that's 1 over 2 to the y. And then I want to get this 2 up on top, so that's 2 to the negative y equals, and we can call this 2 to the 1. So that must mean, I'm running out of space here, but that must mean that negative y equals 1, so y equals negative 1. And so that puts us right there. And I think that's enough to really see what's happening. We definitely are decreasing here, and we know that we've got to approach the y-axis for that vertical asymptote that we know is sitting here. So the only way that that could work is if I did this. All right. So there's a picture of log base 1/2 of x. Now, two very different looks here with these two graphs. And so you might be able to kind of produce a theory here for when it looks like the green one and when it looks like the red one. Notice that the base was less than 1 here, and the base was greater than 1 up here. And so generally, if you're taking the log of a base of x, then if that base is greater than 1, it's going to have this look. And if it's less than 1, it'll have this look. So what we just learned here is really to graph the toolkit function of the log base b of x. Okay. However, we also know how to do transformations. So we learned all these toolkit functions at the beginning of the quarter. And so if we've added a toolkit function, then we should be able to do all the exercises we did with those earlier toolkit functions, which would be graphing transformations. All right, so if I look at what's happening here, we have the base of 3, and so I've got this x plus 2, right? So what is that? Well, it's happening to the x, right? So I'm thinking it's going to be horizontal. And it's addition, so it's a horizontal shift. And it's a horizontal shift, I guess it would be left 2, right? Remember, horizontal being kind of the opposite, so plus means go left. So let's think about what the important parts of the logarithm graph are. It's those couple of points that we talked about, and it's the asymptote, right? Now, normally, the graph of y equals log base 3 of x has a vertical asymptote at x equals 0, right? But if you shift a graph left or right, then you're also going to have to shift the asymptote that much. Just like when we were doing exponentials, if we shifted the exponential up or down, we had to shift the horizontal asymptote up or down. So if I'm shifting left 2, then my asymptote is now over here. Instead of at 0, it's happening at -2 instead. Now, it's important that even though when you put these kind of functions in a graphing calculator, it won't bother to show the asymptote. Make sure that anytime I'm asking you to graph it, you do show the asymptote if it's anywhere besides the y-axis. So you're going to put that there. And then remember what we knew about this, right? It contains 1, 0, and 3, 1, right? Those are the two points that we know for sure are on this base graph here. So the way that I would think about this is when I went over 1 from the vertical asymptote, my y was 0. When I went over 3 from the vertical asymptote, my y was 1. So I want us to think of where our vertical asymptote is now as kind of our new 0. So when I think about it contains this point, I'm going to go over 1 from the vertical asymptote, and y will equal 0 for that point. I'm going to go over 3, 1, 2, 3 from the vertical asymptote, and y will equal 1 at that point. And then at this point, we are confident that it's got this shape to it because the base is bigger than 1, and that's what these 2 points are indicating. So at this point, I feel pretty confident in being able to sketch a pretty decent graph of this function. So just applying that idea of a shift to what we're learning about logarithms. Let's take a look at another one here. So again, and let me go up here a little bit because we can use this same information because I'm using the log base 3 here as well. Okay, so notice in this one, nothing's happening to the x, right? So we have no horizontal shift. So that means that our vertical asymptote stays put, right? It's still right here at x equals 0. All right, but what do we have here? If this negative's out in front, this is going to be a vertical flip. And with this -1, that's going to be a shift down. All right. So what does that mean for us? Well, it means that we have these 2 points, right? When I go over 1 from the asymptote, then my y value is 0 on the original function. Okay? Well, what would a vertical flip do to this? Well, it would do nothing, right? Because my y value is 0. But a shift down would then shift that point down 1 here. All right, and then normally I would be over 3 up 1 from the vertical asymptote. So I'd normally be here. So a vertical flip would put me down at -1. And then a shift down 1 would put me down at -2. And with this, I can confidently sketch what's happening here. Right, I know it's got to have that kind of general shape to it. And if you think of it this way, right, when you flip something that's supposed to look like this, then flipping everything would make it look just like our blue graph here. All right, so I want to take a moment to look at a couple of functions that are already graphed and make sure that we can come up with the equation for them. All right, so here, the first thing I want you to know is when they're showing you some of these graphs, sometimes they might leave the vertical asymptote off, but it should be very apparent what it is. So I think we can agree that what's occurring in this one is that the function is getting really, really close to x equals -4, but not quite there. So let's go ahead and pencil that vertical asymptote in here at x equals -4. All right, so that's good. But what does that mean for the function, right? I'm trying to come up with this function, y equals the log of something, right? So I haven't thought about what the base is yet, but I do know that because my asymptote is 4 to the left of where it normally is, I do know that in here, I put x plus 4, right? That gets me shifted over. Okay, but now we need to figure out what the base should be. All right, so first of all, I can see that if I go 1 over from the asymptote, I'm at y equals 0, right? I expect that. Now, when I'm up at y equals 1, let's notice that this is a distance of 3 from the vertical asymptote. How about when I hit y equals 2? It looks like that happens right here. Okay, so that's 1, 2, 3, 4, 5, 6, 7, 8, 9. So from here to here is a distance of 9. Okay, so what it's looking like to me is if I'm over 3 up 1, I'm over 9 up 2, I'm thinking that my base has to be 3, right? Because, why? 3 to the 0 equals 1, 3 to the 1 equals 3, 3 squared equals 9, right? Which is exactly how far I had to go over to get up to a y value of 2. So this would be my function. All right, let's do one more here. All right, so we've got, it looks like a vertical asymptote at x equals 1. So we pencil that in. And so that means that whatever's going on here, I'm going to have the log of something, but I should have x minus 1 in the argument of the function. So that shifts it over to the right one. Okay, so there's a couple of ways that we could look at this. So let's go over 1 from the vertical asymptote. I'm at 0. So here I'm diving down, right? So there's a couple ways that I can think of this. I can think of it as, okay, when I'm down 1, right, I've gone over 2. When I am down 2, I've gone over 4. Okay. Now, that might indicate to us that we would use a 2 for a base. And in fact, we can. I can go ahead and put a 2 in here. However, we know that if you put a 2 in, you're supposed to go over 2 up 1 and over 4 up 2, right? That's the way it's supposed to go. But instead, I'm going down 1 and down 2 and so on. So what that means for us is that in order to represent this graph accurately, I would have to flip all the y values from what they would be if it was just log base 2 of x minus 1. So if I stick a negative in front of that, then that will give me the flip that I'm looking for. There is another way to approach this same one. Okay, so with, and I'm going to do this in a different color here. Let's see, maybe I'll do yellow. So I could do y equals log, I'll leave that blank, x minus 1. Okay, and so here's the other way to think about it, is to just say, well, bottom line is what happens when I've gone up 1? Well, you can see if I've gone up 1, I'm right here, right? When I'm at a y value of 1. And where is that happening? It kind of looks like it's happening at 1/2. So maybe I can put 1/2 in right here. Okay, but let's test this before we settle on it. Okay, so 1/2, let's think of it this way. Let's go down to one of these points that was a little bit easier for us to make some sense of. So how about -2? So what we want to think about here is, how can I produce a value of -2 if the logarithm is 1/2? Okay, and so my answer had better be if I go over 4, right? That's what the answer had better be. So so let's do, and actually let's go ahead and do this, x minus 1. So just match this exactly. So what we know then is that means that 1/2 to the -2 would have to equal x minus 1. So 1 over 2 to the -2 equals x minus 1, which is 2 squared equals x minus 1. So that's 4. And if I add 1, what do I get? 5. And that's exactly 1, 2, 3, 4, 5. That's exactly the point that gives me a y value of -2. So that's confirmation for me that this would also be an acceptable way to write this graph. So you could go with either one of them. The last thing that I'll leave us with here is the fact that if you wanted to graph these functions to double check your work, it's a little bit tricky. Okay, let me pull up my calculator here. So when you look at the buttons you have on your calculator,
you'll see the common log, so that's log base 10, and you'll see the natural log, log base e. But you don't see just the log of some other base. Okay. In the next section, you're going to learn about something called the change of base formula. And it's a way to take any base logarithm and write it using either the common log or the natural log. Okay, so I'm going to explain in that video why that's true. But for now, just let me just write it down so that you can use this when you're checking on things. So so let's see. We'll put this in its own little box here, separate from everything else. So if I have y equals the log base b of x, then that is the same as y equals the natural log of x divided by the natural log of b. All right, so kind of a strange property here. I'm going to go into more detail with this in the next section, but for now, when you're doing problems like this, you can use this formula to double check your work. So if I wanted to check to see if I was accurate down here, what I would do is I'd say, okay, keep that negative sign. And then I would say the natural log of x minus 1 divided by the natural log of 2. Okay, so the natural log of what's inside divided by the natural log of the base. So if I plug that into the calculator, then I should end up with this same exact picture. Okay, so I'll go ahead and type that in. So negative natural log of x minus 1 divided by the natural log of 2. And we'll go ahead and do zoom standard. And if you look at that, that looks just like what we've graphed. And if you wanted to double check your other one there, when we used the base of 1/2, right? Same thing, the natural log of x minus 1, this time divided by the natural log of 1/2. And if I hit graph, that just lays right on top of the other one. So not only am I confident I did that first one right, but now I'm confident I did the second one right as well, and that those are in fact the same.